In this video, we are going to go over density, what it is, and how to do the math involved with density. So, density is an intensive property. Intensive properties are ones that do not change with the size of the sample. So, whether you have a lot of a sample, let's say you have a lot of gold or just a small little nugget of gold, it doesn't matter that you have a lot or a little. The density of that gold is still going to be the same. The difference between intensive and another type of property, and we'll write it down just because it's good to know, is extensive property. That's the opposite. And that is a property that does change based on your size of sample. So, for example, let's see here, an example of that would be like mass. A small nugget of gold versus a big piece of gold is going to have a different mass or volume. There's a lot of different extensive properties, and there's also a few intensive properties, but there's definitely a lot more extensive properties. So density, it's on your formula sheet that you'll get on a test, and it's just mass over volume. Now, mass has lots of different units. Volume has lots of different units. So what we tend to do is report density in grams divided by liters or grams divided by milliliters. Both of those are common, but if you wanted to, and you wanted to represent your density in teragrams per nanoliters, that's not wrong. It's just not a normal way to do it because density is just mass over volume. So as long as you have a mass unit and you have a volume unit and you divide them, that is an acceptable way to represent density. Now, one thing that I don't know if it's come up so far in this unit, but a milliliter, ml, is also a cubic centimeter. And a cubic centimeter, that's just going to be centimeters to the third power. You may have seen in like medical TV shows, or if you've ever been in a medical environment, doctors and nurses might be like, they might say, I need 5 cc's. Well, what they're really saying is they need 5 milliliters, and where cc's come from is just cubic centimeters. Okay, so there's lots of ways to determine the mass of something, but the easiest way is let's just put it on a scale, okay? That's not going to be difficult. But volume can be difficult, especially if you have an irregular shaped object. So I'm going to try my best to draw a cube. If we have a cube, we could just do length times width times height and get the volume. But oftentimes in science, especially chemistry, we're not given just cubes of something or three-dimensional regular shaped objects. Most of the time they are very irregular. And so what we're going to do when that happens is we're going to do something called water displacement, okay? And sometimes this is just called displacement because it doesn't have to necessarily be water. And what we're going to do is we're going to fill up a graduated cylinder with an amount of water. And this looks like it's 40 something milliliters. And then when we put our sample in there, this is our sample, we are going to see that the water gets displaced or it rises. And the difference in volume is going to equal our volume of our object. Okay, that's a nice, easy way to do this. So let's practice some math here with how to solve density. Now, as we work through these, I'm not going to necessarily do all the examples in your notes because the key to this is posted online, but I want to do the ones that I think are weird or that are great examples to get you started with density. When you read a question in any chemistry context, whether it's density or something else, I think you should be underlining what you're given and circling what you're trying to find. Additionally, if you are using a formula, in my class, you always get a point for writing down the correct formula you use. So whether you know how to solve it, that's important, but you should always be writing down the formula, because if you don't know how to solve it, that's a bummer, but at least you'll get a point. So question 1 says, what is the density of wood with a mass of 2,200 grams and a volume of 2,400 cubic centimeters? So I'm going to say density equals mass over volume. I'm going to plug in what I know. 2,200, that is a mass, and 2,400 cubic centimeters, that is a volume, and so I'm going to get 0.91667 grams per cubic centimeter. Now thinking about significant figures, which I hate thinking about, but we've got to do it. This guy, decimal is absent, so we have 2 significant figures. This guy, decimal is also absent, so we have 2 significant figures. So we'll round this off to 2 sig figs, and we'll get 0.92 grams per cubic centimeter. Okay, when we multiply and divide, which here we're dividing, we are going to end up with the same number of sig figs as the number that has the least amount of sig figs. So in question 2, it says, using your answer from number 1, will this piece of wood float when placed on water? And I don't know what happened with my apostrophes here, but water's density is 1 gram per cubic centimeters. You just should know that density. So I'm going to say yes. The wood will float and this is because objects will float on substances that are more dense than the object. So water has a density of 1 gram per cubic centimeter. This piece of wood has a density of 0.92 grams per cubic centimeter. The wood is less, therefore it will float. Now, be careful when you use this. Just make sure that your units, they've got to be the same. If you're going to have a legitimate comparison, the units, they should be the same. Okay, now let's look at number 3. It says, what is the mass? So we'll circle what we're trying to find, of 25 cubic centimeters of gold. And I give you this unit, and it says gold's density is 19.3 grams per milliliter. Okay, so I'm going to write my formula. Density equals mass over volume. And I'm going to plug in what I know. So we're given the volume, 25 cubic centimeters. We're asked for the mass, so I'm just going to put X there for the mass. And then the density, watch how I'm going to write the density. I have 19.300 grams for every 1 milliliter. So does this make sense that 19.300 grams per milliliter is also the same thing as 19.300 grams for every 1 milliliter? You don't need to show the conversion of milliliters to cubic centimeters here just because it's 1-to-1. It's a very easy thing. So what I'm going to do is just say that this is 19.3 grams for every 1 cubic centimeter. Ask yourself how you're going to solve this expression. One thing that's important to know is because we were given grams in this numerator here, when I solve for x, it's got to be in grams as well. That's the only way to get this math to work out. I am going to cross multiply. So I will multiply 19.3 times 25, and when I do that, I get 482.5. Can't write, 482.5. That equals x grams, and so that is our mass, 482.5, but with significant figures, we have, let's see here, We have 5 significant figures, and we have 3. Since we're multiplying and dividing, we'll go based off the least number of sig figs. So this will end up being 483 grams of gold. Okay, go ahead, pause the video. You can try out number 4 on your own. Here, and I'm going to work through it, so just pause it, try it out, make sure you can do this. We have density equals mass over volume. We are given 121.5 grams. We are given 45 cubic centimeters. And that works out that is 2.70 grams per cubic centimeter. My sig figs are good because we had 3 and then we had 4. We'll go based off the least amount. They ask, will this substance float on water? The answer is no. The substance is more dense than water. Will this substance float on mercury? It looks like it will. Yes. This substance, which I think is aluminum, is that on here? Yeah, it looks to be like aluminum. Yes, this substance will float on mercury because the substance is less dense. Than mercury. Okay, let's see which ones we should do. Okie doke. I want to look at, and I'm going to change this one. I want to change number 6. So make this change for me because I want you to know that you can solve one where you're solving for something in the denominator. So we're going to use the table in problem 4 to determine the volume. I'm going to change mass to volume of mercury that has a mass of, let's just say, 50.0 grams. So let's use a table. When I flip back to the table, the density of mercury is 13.550 grams per milliliter. Density is equal to mass over volume. And I'm going to plug in what I know. 13.500 grams for every 1 milliliter. We are given 50 grams. That'll be our mass. And we're going to solve for our denominator. Because on one side our volume is in milliliters, we'll need milliliters over here. I'm just going to cross multiply. So I'm going to cross multiply, and I'm going to running out of room here, so I've got 13.500x equals 50 times 1, which is 50. Divide each side by 13.500. And x, let's see what that's going to be. I could probably do it in my head, but might as well use a calculator. We're going to get 3.70 as our answer. And I rounded it that way because we have 3 sig figs, and then here we had 5. So I wanted to cut it off at 3 because that was our least amount of sig figs. And that will be milliliters. Okay, I want you to look at number 8. It says water has a known density of 1 gram per milliliter. If a student in the lab measures a sample of water as having 79 grams and occupying 85 milliliters, what is the percent air? So I gave you this formula, and on the test you'll have a question that uses this formula, and the formula will be given. So let's just practice how we're going to use this. Density is equal to mass over volume. What I'm going to do is I'm going to solve for just what the student would get for their density in class. So 79 grams over 85 milliliters. And they get 0.93 with sig figs grams per milliliter. Plugging that into percent air, we're just going to use this value. Make sure you understand that these are absolute value bars. So whatever you get, you're always going to get a positive answer for your percent air. So the value we got is 0.93. The accepted value is just what's known. Sometimes this accepted is even changed with known. So minus 1 divided by the accepted value or the known value, and then times 100%, absolute value. And when you do this, you're going to find that you get a 7% error. Okay, we're going to do 2 more questions. We're going to do number 9 and then number 10, which has a dinosaur in it. So, in number 9, it says the density of gold is 19.7 grams per cubic centimeters. If a 2.5 kilogram rectangular block of gold has 2 dimensions of 3.7 and 6.5 centimeters, calculate the third dimension of the block. So, I know density equals mass over volume. I'm going to plug in what I know. I know the density is 19.7 grams for every 1 cubic centimeter. The problem is we are given 2.5 kilograms. So that can't go here because the units need to be the same for my numerator and for my denominator. So because we've already learned this, I'm going to convert 2.5 kilograms. I'm just going to go ahead and convert it to grams. So kilograms to grams. Kilo is a prefix, so 10 to the third, and we get 2,500 grams. So now I'll plug that in. And then for our volume, we have a rectangular block, so that might look something like this. And we've got 3.7 centimeters, 6.5 centimeters, so maybe we're trying to figure out the height, maybe. So we know length times width times height gives us a volume, so let me plug in what I do know. We've got 3.7 centimeters, 6.5 centimeters, and I'll just call the last dimension, which is what we're trying to solve for, as x, and it'll be in centimeters. So we're going to cross multiply. I'm going to take 19.7 times 3.7 times 6.5, and I'll plug that into my calculator now. I get 473,785, and that equals 2,500. One thing I forgot is the x also gets tagged along there. We want to isolate the x, so we're going to divide by the side or the coefficient that has the x. So 2,500 divided by 473.785, we're going to get 5.27665 centimeters. Let's look at sig figs. 3 sig figs, 3 sig figs, 2 and 2, so we want to cut it off at 2. That'll round up to be 5.3 centimeters. Okay, I know this video has been kind of long. I just want to make sure you're good at density while you are filling in your notes, because it shouldn't be something that you have too much of a problem with, so long as you make sure you are asking questions and doing the practice. So here, this is a problem with displacement. So the volume of a dinosaur can be calculated using water displacement. If the mass of the dinosaur is 3.5 kilograms, what is the density of the dinosaur in grams? So I'm going to first take 3.5 kilograms. 1 kilogram is 10 to the third grams, and so I'm going to get 3,500 grams. Density of dinosaur is mass over volume. Which they asked for grams per liter. So that's why I went and got it in grams. Now I'm just going to figure out how many liters this is, and it's marked in milliliters, so that'll be important. If I estimate this is 4.8 milliliters, and then this is these are by 0.2s, which is really weird. This is 5.6 milliliters. And so if I take 5.6 milliliters and I subtract the 4.8 milliliters, initially, I'm going to get 0.8 milliliters is the volume of our dinosaur, which is a very small dinosaur, okay, not even a milliliter. But they asked for liters, so we'll take 0.8 milliliters. We'll go from milliliters to liters. 1 milliliter is 10 to the minus third liters, so 0.8 times 10 negative 3. We get 0.0008 liters. We'll plug that in over here. So 3,500 divided by 0.0008. And I'm going to use scientific notation here because it was a big number. It was like 4 million something. So 4.375 times 10 to the 6 grams divided by liters. If we were doing sig figs here, which this one's a little bit weird to be doing sig figs, we have 2 sig figs divided by 1 sig fig. So this would actually just simplify to be 4 times 10 to the 6 grams per liter.